Okay, here's our GitHub page. I'm going to take a walk through of our Jupyter Notebook file and just kind of give a high-level synopsis of our approach. All right, so we imported all of the necessary packages from scikit-learn, as well as Seaborn, Keras, and NLTK. Okay, so our whole approach here was to solve the business problem of helping dispensary owners determine which strains of cannabis would make sense to stock. Our analysis has provided some valuable insights for this, and we've produced a workable model that I'll be going through in this video in order to achieve that objective. In the first section of our analysis, we explored the data and we did some data preparation. Since most of the features, as you're going to see, that we had to work with were string and categorical, we had to use the NLTK library extensively. There are numerous visualizations in order to understand the data set. Okay, so did a basic describe, went through some summary statistics. Just quickly off the top here, we noticed that the mean and the standard deviation show that the data is not very spread out. It's very densely populated, around 4.31. In fact, the median is actually 4.4, showing us that it's highly skewed data. As I said before, the features that we have to deal with are strain, type, rating, effects, flavor, and description, where our target variable here is rating. Type, strain, effects, flavor, and description are all strings. So first thing that we decided to do is we decided we needed to transform our target variable to make it more useful for our models. This was required because users who had submitted their descriptions, as I said before, they are highly skewed. Everything is sort of between 4 and 5 on a 1 to 5 scale. This meant that a successful regression would end up predicting nearly the same value for all of the strains, which is obviously not something that we wanted to do. We want to have value come out of this. So in order to overcome this, we transformed the target variable, the rating, by separating the samples into bins based on their scores. These bins represent strains that should not be stocked, that should be considered, and that should definitely be stocked. This allowed us to approach the problem as a classification problem rather than a regression problem. It also had the added advantage of making our model's inputs more intelligible to end users. The results are more intelligible because the shop owner would be better served with the class telling him to keep it or to reject it. Getting back into some of the data cleaning, we noticed that there was duplication in some of the strains. So we searched for duplications and we removed them because obviously we do not want to have the same data point duplicated in our data set if we can help it. Through exploring the data, we looked by type. There are 3 types: hybrid, indica, and sativa, just to kind of get a feel of how these different features interact with everything. This is a box plot. Again, this is a really good way of visualizing how tightly packed the data is, right around that 4 to 5 range. We had to clear null values from flavor. Okay, and then after deleting the values, we are converting the data types from strings to lists, as that would be the final format that we would need them to do our analysis. So you can see here the rating bin that I was talking about. Right? So this is less than 4.2, in between 4.2 and 7, and greater than 4.7. Just looking at this quickly, you can tell that it's an imbalanced data set, which led to the next point, is that our data is unbalanced. The data as we found it had nearly 60% of models in one class, right? When the models were run using this unbalanced data, they all eventually determined that the best model was the one picked the overrepresented class, and by doing so, it achieved a 60% accuracy. In order to fix this, we oversampled the underrepresented classes, so the 0 and the 2, so that the data had roughly equal balance between the three classes. All right. So here's a little bit of visualization that we did. Visualizing the effect of flavor. All right, so this is breaking it down by bins. And you can tell everything is very much centered around that center bin. So all of this analysis was done before oversampling. Visualizing flavor. This is the flavor profile. And again, everything is around that center bin, which is not surprising. Right, so we did a very thorough analysis here of all of the different flavor components. Okay, so the next thing that we did was we looked at the effects in flavor in a more broad sense here. So one of the things that we wanted to do to make our code more reusable is we defined a lot of functions to do the monotonous tasks that should be automated. So we created a pivot table for rating and effects, and this allowed us to generate the tables below, which is looking at the effect. So it's a total live count of the rating by the effect type, right? So if we look here quickly, we can see type 4 and 5 generally make people feel euphoric, happy, relaxed, and uplifted, which makes sense. These are the general things that people speak about when they're referring to their time enjoying cannabis. Then we looked at the flavor profile breakdown, right? And there's two that jump out here. And again, it's the 4 and 5 classes, which is not surprising given that most of the data is within the 4 and 5, right? And that's illustrated in this table here, where 4 has 696 hybrids and 5 has 421, with the other two flavor types being fairly similar in the amount. And then when you look at 1, 2, and 3 ratings, there's almost no data for that. As we spoke about in our presentation, in our class, if you haven't heard that, one of the things that we would like to see from this data set is more additional data in the 1, 2, and 3 rating categories so the data can be a little bit more balanced. It would make the analysis much more meaningful, and we wouldn't have to approach oversampling in the way that we did. All right, and then finally is looking by type, where hybrid has the most things. Okay, visualizing the descriptions here. So just looking at the description length. So everything is kind of centered around 400 here, and it's a frequency chart. The average length of the description is 454. And then this is the distribution length here. And this is by the bins. So when you look at bin 1, which has the majority of the data, right, it takes over most of the graph. Or 0 here, you can kind of just make out the red line in the center. It's more tightly packed. Okay, so the next thing that we wanted to do is we wanted to look at the words that are used in the description. The description is a feature that did most of the heavy lifting for our analysis. So we wanted to get a sense of, okay, what words pop up the most here. So at the beginning, before doing anything with stop words, the words that pop out are genetic, strain, flavor, sativa. And then within that, there are some stop words like that really don't provide much meaning. So in the next step, we handle all of these stop words and create a new visualization here, which we felt had more meaningful words. Right? So now we have sweet, haze, purple, potent, flower popping up. So these are more descriptive terms that are different than just the filler terms. Okay, and then we looked at it by the rating, so by our bins. So in bin 0, we have body, we have sweet, flower, citrus, strong, potent. In bin 1, we have sweet, haze, potent, purple, uplifting, strong. In bin 2, body, sweet, potent, consumer, citrus. Right? So you kind of get a feel of the different words that are thrown around for the different rating bins. And this is what we wanted to help guide the shopkeeper to stock the correct product. Okay, so here, one of the most basic pre-processing steps is removing null values and fixing data types. And then, as I said earlier, oversampling or undersampling for imbalanced classes. We oversampled. We have class 0 and 2, which do not have enough samples in them. So we essentially just had to generate new values and plug those in to rebalance out the data. Right, so you see the new graph here, 0, 1, and 2, they're much closer. And this is what we need to do our analysis. So moving on to the second section, we're building off of the insights from the first. Because all the features were text, our approach was different than if it was just numerical features. Right, so now we're getting into the NLTK cleaning, where we write a function to make all the words lowercase. We remove stop words, punctuation, special characters, we stemmed words, and we tokenized words where applicable. So that's kind of what's going through here. After this, we're getting into 2 data preprocessing models. The first is scikit-learn's count vectorizer. And the second is GenSim's word2vec. So the first count vectorizer we used to clean sentences into numerical features, and then we used TDIF to get the importance of each word in that data set. So the second, which is GenSim's word2vec, was we built a 1-layer neural network to predict probabilities of words appearing near each other in the data set. With this model built, we extracted the word embeddings, the weights in the hidden layer for each word, and then reconstructed the feature matrix by taking the mean of each word's associated vector. Once all the data had been cleaned, we applied the same 4 models to both preprocessed feature vectors. These models were KNN, random forest classifier, SGD classifier, and a neural network with Keras. So that's what I was just scrolling through here. Right, you can see the Keras model here. The scikit-learn models were all tuned with 3-fold grid search on the 2 data sets, and were optimized for each of them. The Keras model was built using 4 hidden layers, 5 nodes each, and the ReLU was used as the activation function. So if I scroll back up, this is our Keras model here. All right, so we're training the data, fitting up the model, using our ReLU, compiling, training, running it through the epochs, predicting, right, and then measuring our model. So all the models were evaluated on their training data using 3-fold and 10-fold cross-validation. Using this, we were able to ensure that the models were not overfitting. These models performed similarly on both pre-processed data sets, so that GenSim and word2vec. However, the data pre-processed with scikit-learn had over 10,000 columns in the feature matrix, while the one pre-processed with GenSim only had 100. Because of this, we determined that the GenSim model of getting the feature matrix was superior because it produced comparable results with far less training time. So getting into the accuracies here a little bit. So the accuracy for the random forest model was 0.82. Right, and these are the two approaches. So I'm just scrolling through the second approach. Okay. And 0.84. Okay, so we have two different values because 0.84 was run through GenSim, and 0.82 was run with scikit-learn. So we ran a total of 8 models because we used 2 pre-processing approaches. So as you can see, the SGD, the KNN, and the KERAS models all performed fairly poorly. They all performed less than 60%, which is not ideal. And the train set and test set accuracy were similar in all the cases, using both 3-fold and 10-fold cross-validation on the training sets. The KERAS model was improved to show as high as 70% accuracy on the test set, but this came with a training set accuracy of 99%, which is obviously an example of overfitting. As I pointed out, the random forest model had a very good accuracy of greater than 80% in both cases. So our findings from these models is that only the random forest model was able to successfully capture the complexity in the feature matrix without overfitting the data. However, its accuracy needs to be taken into perspective because the dataset was modified to oversample the underrepresented classes, so the 0 and the 2. It's almost certainly the case that the test set contains some data which was duplicated from the training set. Furthermore, the random forest model performed worse with 3-fold cross-validation, around 72%, and second worst with 10-fold cross-validation, around 78%. It performed the best on the test set, around 82%. So the accuracy range you're kind of looking at is between 72 and 82%, which, given this is our first approach on something like this for natural language processing, that's a fairly good accuracy range to be working within. The tables below show the 2 metrics for the 2 methods of preprocessed data. So looking at scikit-learn, I'm just scrolling down to the correct table. I just need to find it here. Right, so this was our scikit-learn for the random forest. And you can see that essentially all of the values are around what we would be looking for. They're all fairly in line with each other, which is great to see. So taking this all into account, we feel fairly confident that the random forest is a good working model and it has the potential to perform well in the proposed business context. Our recommendation is for the dispensary owners to use the random forest algorithm to test proposed strains based on user input so that they can determine which to stock. In order to improve the model, as I stated before, one of the best things that we can see is additional data so that we can deal with the underrepresented classes. This would improve the model's performance, and it would also prevent us from needing to oversample, which would be fantastic. Secondly, the model would benefit from further hyperparameter tuning. Given the complexity of the model, we had very high n estimators and high max depth. The random forest classifier took an absurd amount of time to perform grid search. A possible improvement would be to be doing a randomized search on a greater number of hyperparameters, in order to determine where to focus the full grid search, as the grid search takes a crazy amount of time to run on this data set. And in summary, that's our model. You can find it on our GitHub page under ml_final_cannabis.pynb.